So welcome everyone. Good morning, good afternoon, good evening, wherever you are in the world. So I would like to welcome you to this webinar with the title Multispectral Imagery in Agricultural Research from Theory to Practice. And with me today, we have special guests from the Swedish University of Agricultural Sciences who will share their experience using multispectral imagery, Mats and Kristin. But first, I would like to start with the agenda and a few housekeeping rules. So this webinar will consist of 4 main parts. I will start in the beginning with the introduction to the basic concepts of what is multispectral imagery and how it works. Then Mats will dive deeper and talk a bit about vegetation indices, and then also about the tests that we have done last year, where we collected multispectral images using different sensors and took pictures of different types of calibration panels. The goal of those tests was to compare the data and see if there are any differences. So we'll share the results of those tests. Then after that, Kristin will share a practical example from one of the research projects at SLU, where they have been using drone imagery and multispectral sensors mounted on drone images in small-scale trials to develop the models that they then scaled and used together with satellite imagery. And finally, after all the presentations, we will have a Q&A session where you can post the answers. So post the answers during the presentations in the chat below, and in the end of this webinar, we will try to answer as many questions as possible. All right, let's start with a round of introductions. So first, Mats and Kristin, can you please introduce yourself and tell us a bit more about the work that you're doing?
Yes, hello. My name is Mats. I work with the Swedish University of Agricultural Sciences. And as you can see, Sweden is far north in Europe. And the University of Agricultural Sciences, we are distributed over a large part of the country. And we are located in a campus in a small town called Skara. And we work with the Department of Soil and Environment and with a group with precision agriculture and pedometrics. So I'm a researcher there and working with remote sensing, digital soil mapping, and other related things.
Hello, and I am Kristin, a colleague of Mats in the same campus here in Skara. I'm a biologist and a senior lecturer here, and my research interests are how crops respond to various spatially and temporally varying conditions, and how to measure and monitor conditions and adapt management accordingly to optimize production. That's interesting.
Great, thank you. And you have been using drone imagery in your research for quite a while, right? When was the first time that you started using drone imagery?
I think we started in 2005 with some initial tests with a company called Smart Planes.
Yeah, also a Swedish company, right? Yeah, so that was quite a while ago, before the most drone companies even started. I came in touch with Mats back in 2015 when I started Solvi, and that's kind of how Solvi was born, essentially, out of the collaboration with the Swedish University of Agricultural Sciences. So already back then, Mats had been using and Kristin been using drone imagery for quite a while. So I joined them and during the data collections and was helping to collect and process the imagery. You can see here in the left image is the kind of drone that they use from this Swedish company, Smart Planes. And already back then, they've been trying different advanced multispectral sensors with 8 bands, I think, in this case. Then there in the middle is the drone that I've been flying back in the day. So there was no DJI Mavics with multispectral sensors where everything is nicely integrated. You had to kind of assemble it itself. So that was my first drone, 3D Robotics Iris Plus. And we used a GoPro camera for RGB imagery and then Mapier sensors for multispectral imagery. So that's how Solvi was born, and I'm the founder of Solvi, as you already understood. So we started with a pilot project together in 2016 where we developed a prototype for making the process of processing the drone imagery and then extracting meaningful agricultural insights from it as easy as possible. And that's how Solvi was born. And then the official release of Solvi was back in 2017. And then from there, we developed different tools and features that many of you are familiar with and use today. The flagship feature is our Plant AI tool that you can use to train your own agricultural AI models to do different types of analytics, like counting the crops, extracting plant level data, like the size and the health of individual plants. But also in the latest month or years, more and more customers use it for all types of different use cases. And for example, detect the weeds in the field and calculate the weed coverage and so on. So possibilities are quite big. And then the second area of analytics that Solvi offers is tools for the field trials. So that's mainly used by researchers, both within educational and commercial research and breeding, where you can easily digitize the plot boundaries and then extract a lot of different metrics, including different vegetation indices, plant counts, and so on. So that's briefly about us. And let's dive into the topic of this webinar. And I would like to start with the basics and talk about what is reflectance, because I think it's a very important concept to understand before we dive deeper into vegetation indices and so on. So reflectance in simple terms is essentially the amount or percentage of sunlight that is reflected when it hits the surface of the Earth. And on this image, we can see how it's reflected by vegetation. So the green, red, and blue pillows represent the part of the light that we humans see with the naked eye, so visible light, RGB. That's also what RGB cameras capture. And as we can see, the differences are not very big. We can see that the healthy vegetation reflects a little bit more green light. That's why healthy vegetation also appears greener. But then also there are parts of the light or parts of the light spectrum that we humans can't see. And that's what this black arrow represents, the near-infrared light. There it happens a lot more when it comes to analyzing the vegetation. And that's why it's so commonly used in multispectral analysis. If we move on to the next slide, this is another way of looking on the different types of light. So you've probably seen graphs like this, which represent the electromagnetic spectrum. So on the x-axis, we see different parts of the light spectrum. And again, blue, green, and red light is what we can see here. And it's measured in the nanometers. So this different wavelength here show where one part of the light spectrum starts and another and ends, and then where another starts. We can see that the different objects reflect the light differently. So in soil here, for example, there is nearly no difference in reflectance across all the different spectrums of light. When it comes to vegetation, we can see here again this small bump in the green spectrum, but otherwise this curve is pretty flat. But then what's interesting is this steep curve in the reddish and near-infrared spectrum. That's where a lot of things are happening, and that's why these parts of light spectrum are so useful in the remote sensing and analysis of the vegetation. So on this chart, this is similar diagram showing the light spectrum, but what we can see here is that not only different objects reflect different parts of the light differently, but also if you look just at the vegetation, the reflectance varies depending on the crop status or crop properties. So healthy vegetation will reflect more light, less healthy reflect less light. And that's really what remote sensing and analysis of multispectral imagery is all about, looking at these variations in different parts of the light spectrum. But we can also see here that although this part of the spectrum here is most commonly used in the research, there is a lot more data available in other spectrums that can be correlated with properties like water content and so on. So So that's reflectance, and what the different sensors and cameras measure is exactly that, the reflectance. So here we see, we have a look at the Sentinel-2 satellite sensors that measure multiple different parts of spectrum. So this is what these small bars here represent. So everything from the blue, green, red light here, all the way to near-infrared, reddish spectrum, and even further than that. If you look at the different drone-based sensors, so sensors like MicaSense Altum and RedEdge, but also Mavic 3 multispectral, that is very common nowadays. They measure also different parts of light spectrum, but here is the important thing to understand is that what they measure is slightly different. So when we talk about red light, for example, here we can see that MicaSense measures this range here, Mavic 3 measures slightly different range. When it comes to the red light, it's not that crucial because the reflectance here is roughly the same. But in other parts of the spectrum here, red edge and infrared, the differences are much bigger. So especially in red edge, we can see that this curve becomes very steep, and Mavic 3M measures this part, while MicaSense Altum and RedEdge measure completely different, and the differences can be quite significant. So you can measure with both cameras the same crop at the same time, and one will show you 15% reflectance here, and the other will show you 25. And neither is right or wrong. It's just that they measured slightly different parts of the spectrum. So that's really important to understand when analyzing the imagery, and especially when you apply some very specific models that are developed during the research, something that Mats and Kristin do in their work, where they develop these models assuming specific wavelength, specific parts of the spectrum. So when you try to apply this model then in practice and use drones and sensors, it's important to be mindful that if you want to use those models as they are, you need to also use the same data. So drones essentially measure the reflectance, and one way looking at it, like how it practically works, you know probably that the images consist of pixels, and in each pixels there are numbers. So the reflectance is usually represented by the digital numbers in every single pixel. So if you open, for example, a drone image in QGIS and use the info tool and click on the individual pixels, you will see that there will be a number for individual band. So that number represents reflectance. You can translate that digital number by dividing it by the maximum value of that range that the imagery is in. So RGB cameras usually use 8-bit format, so the max value is 255. So if you want to calculate reflectance, you just divide the pixel number by max value and you get 0.27, so 27% reflectance. Multispectral imagery usually uses 16-bit range, and usually half of that range is reserved for reflectance. So half of that range, the maximum number will be 32,767. So if you take a number, divide by it, you will also get the reflectance. So that's how it works in practice, and that's what the images that you capture with the drone represent. Now, when collecting these images, it is really important to consider the light condition during the time of the collection. So many times, especially if you're working with research and collecting imagery over different field trials, you want to compare the data over time. But then also, if you're doing work like Mats and Kristin, who use the data from the different sensors and even used these types of analysis done on satellite imagery, you want this data to be comparable. So that's why it's important to consider that the light conditions can be different, and it affects the reflectance. And to correct for that, to take that into account, so that you can actually compare the data no matter when you collected it and which sensor you used, you need to do the calibration. And there are two different ways of doing the calibration. So first of all, on most drones, there is a light sensor that sits on the top of the drone and records the amount of light that is coming in from the sun, and stores that data in the metadata in every image. So that information then can be used during the processing to do the necessary corrections. Another way of doing calibration is to use the calibration panels that are placed on the ground. So here we can see MicaSense panels, and this is panels that SLU uses, custom made by a company from Finland. And the idea here is that these panels have known reflectance measured in the lab. So before and after the flight, you take the images with the drone of these panels, and then knowing their reflectance, you can calculate what kind of corrections you want to do to the images to take the different light conditions into account. So those are two different main methods. In most software, when you process drone imagery, this is taken into account. So you need to just either choose one or another method or both. In Solvi, it's pretty straightforward. So if you don't have a panel, you just upload the images, and you can tick here during the imagery upload if you want to use the data from the DLS or sunshine sensor or not. If you have a panel, you take images of the panel like Mats does here on this image, so before and after the flight, and then just upload the images of this panel together with the rest of the imagery, and this will be automatically recognized during the data collection, and the algorithms will read the reflectance from this little square here on the panel and apply all the necessary corrections based on that. That's how the calibration works, and this is what I wanted to talk about when it comes to reflectance. Next, Mats will continue and dive a little bit deeper and talk about how the reflectance values can then be used to calculate different vegetation indices and do more advanced type of analysis. Mats?
Okay, so I will try to talk a little bit about this thing with vegetation indices, and it's a very central part of remote sensing, of course. And in the upper part of the picture here, you can see that some examples. There are different types of vegetation indices, and they are like trying to pinpoint various crop properties when we talk about agriculture. And certain parts of the spectrum is better than other parts for certain things. And so, for example, water stress indices, often it's very useful if you have some information in the shortwave infrared region. And some indices use, for example, this band over here together with the near infrared to make an assessment of the water stress then. And then we have another type of indices, which are the red edge indices, and they have bands in this part of the spectrum, and they tend to be very useful for example, chlorophyll concentration, nitrogen content in crops. And then the more, can we say, traditional indices are based on the near infrared and the red part, and DVI, for example, and typically very useful for biomass predictions. And then we have RGB indices that are based on the visible part of the spectrum. So if you have an ordinary digital camera, you can do some indices also by using the red, green, and blue bands. So there are certain indices. There are so many index you can choose between, and there are certain indices that are developed for trying to describe different things. But drones generally are using only this part of the spectrum. So there's not so many. There are some hyperspectral cameras that are using this part of the spectrum, but most commonly the drones that are used are focusing on the visible to near infrared region of the spectrum. And this was a slide that Igor showed before. I wanted just to highlight, for example, the most important sort of common index, normalized different vegetation index, uses bands in the near infrared and the red. And it describes the difference here in reflectance, which is very large between the red and near infrared. So, and then if you look at the normalized difference red edge index, which is a similar type of index, but uses bands in the near infrared and the red edge part, then you get some other calculations. And the advantage of NDRE compared to NDVI is, for example, that it doesn't get saturated as NDVI does if you have a high biomass and a very, very sort of good crop. Then NDVI tends to approach 1. So it doesn't give you so much information when the crop is really growing well. So there are many different indices, and if you look in the research literature, you would find that some of these they have been used for people are trying to use it for almost anything. It depends on what kind of sensor you have, more or less. So NDVI can be used for many things, but of course it's mostly efficient maybe compared to other indices for biomass, and some other like index is very much efficient for nitrogen uptake in a crop. But still, they are very correlated to each other. So they are not really a perfect measure of a certain crop property. So you can expect that everything is correlated with each other, but to a different degree. So if you plan to use a drone and fly and take images and make a mosaic and use it for a specific task, for example, okay, I want to calculate the amount of nitrogen that the crop requires based on my drone image, then you need to do some kind of assumption. You need to assume that nitrogen is limiting. The variation that I see is dependent on nitrogen. And in that case, calibrations are needed, or you need to do some sort of work in beforehand so that you can reduce the amount of variation caused by other factors. Because it's very difficult with these indices, a single index, to distinguish between different types of variation that you can see. So if it's water or if it's something else that it's causing some variation, then it might be easy to interpret it as it's something else, like nitrogen, for example. So it is very important to understand that these indexes, they are quite crude measures in a way. So it's important to try to calibrate with real observations as much as possible. So in this comparison that we did last year, we used 4 different cameras, the Mavic Multispectral, and we used the MicaSense Red Edge and MicaSense Altum, and also a camera called Maya, which is a 9-band camera from a company Eoptis in Italy. And those bands are similar to band 1 to 8 plus 8A in Sentinel-2. So it has the same specification. So that's a bit interesting. And we did fly onto locations. It was at the research station outside Skara here, over a pea field. And we also did fly over a private farm close by, a potato field. It was in August last year. And as you can see, the crop was there was different varieties here. Some part was quite green, but as other parts started to wilt, and it was quite late in the season. So it was a lot of variation in the field. So it was good for just testing and comparing cameras. If we look at the spectral signature that you get in different parts of this potato field. So for example, here in this the more green crop, then you have a spectral signature from the Maya camera in this case that looked like this: a very high reflectance in the near infrared and low in the visible. And if we look at another spot, we can see that the near infrared is much lower. There is some difference here in the visible, not so much. And if we look at a very brown part, then it was very low in the near infrared, but still some small differences here in the visible. So as you can see, much of the variation happens here in this part. So it's really important to have information in that part of the spectrum. If we look at the NDVI index from different cameras over this field, so the Altum camera looked like this. Blue is high and the brownish is low. We look at the MicaSense Red Edge, you can see that it's extremely similar, which is nice. We hope that it shall be sort of similar when we fly with these good cameras. And actually all the cameras produce something that is you can, by the eye, it's very similar actually. And that is nice. If we instead change to fixed classes and not the relative classes, then we can see some differences. The Altum and the red edge are still very similar. They give the same values. This camera, the Mavic 3M, is a bit lower. And the Maya camera is slightly higher than this. So there are some differences when we use the drones and we use the approach that is suggested by the manufacturer to calibrate. This is the same thing, but in a some histogram instead. So you can see that the Mavic 3M is a bit lower, the average index. Those two cameras were similar, and this one was actually, yeah, this was a bit lower in this in the points that we compared with. And if we look at more indices, this is the NDRE, this is the green-red vegetation index. And these two are calculated in the same manner as this one, but with other bands. So it's just the same equation. And then we have another index, which is a bit more tricky to compute. It's based on the near infrared and red bands only, but it's a more strange equation. So some differences will be maybe more pronounced if you have more different values in the near infrared, for example. It will be more pronounced when you use this type of strange equation compared to just a quotient like this one. And actually, all the cameras produce something that is you can, by the eye, it's very similar actually. And that is nice. If we instead change to fixed classes and not the relative classes, then we can see some differences. The Altum and the red edge are still very similar. They give the same values. This camera, the Mavic 3M, is a bit lower, and the Maya camera is slightly higher than this. So there are some differences when we use the drones and we use the approach that is suggested by the manufacturer to calibrate. This is the same thing, but in a some histogram instead. So you can see that the Mavic 3M is a bit lower, the average index. Those two cameras were similar, and this one was actually, yeah, this was a bit lower in this in the points that we compared with. And if we look at more indices, this is the NDRE, this is the green-red vegetation index. And these two are calculated in the same manner as this one, but with other bands. So it's just the same equation. And then we have another index, which is a bit more tricky to compute. It's based on the near infrared and red bands only, but it's a more strange equation. So some differences will be maybe more pronounced if you have more different values in the near infrared, for example. It will be more pronounced when you use this type of strange equation compared to just a quotient like this one. And as you can see with this near NDRE in the indices, they are quite different to some extent, especially the Maya camera is different. And that's not so strange because the Maya cameras, the bands used here are fairly different. We used the band 7 and 5 in this case, and band 5 is quite low reflectance compared to these, the red edge band that is available in these cameras. So that means that it becomes different. And that's something to think about, that NDRE itself, it's not a good thing to just say NDRE. You need to specify what kind of bands you are using really, and what the wavelengths are, because it can be very different depending on the camera. The green-red index also varies a lot, and that could be because of the reflectance is very low in the green and red bands, and some differences, even though it might not look quite much, is can be quite large in an index still. So there could be quite large differences in the green-red vegetation index. And here also the Mavic 3M is a bit lower than the others, you can see. But even if they are different, they are correlated to each other. So if we compare these two examples, it's actually this one. Yeah, okay. You can see that they are well correlated, although they are not perfectly correlated. So it's not the same value, but it's still there's a strong correlation. So and it's the same also here, that these cameras produce something that is very similar, but to some extent different. If we look at one of the drones here, Mavic 3M, and different calibration methods, what happens? If we don't do any calibration at all, we just use the images as they are, then you get very funny values. So that's not something that you should do. If we only use the incoming light sensor for calibration, which is what you're supposed to do with this drone, because it doesn't come with any reflectance panels or anything. It has this incoming light sensor, and that's what you are supposed to use. Then those bars in the green, red edge, and near infrared, they are actually a bit lower. It was in both our tests here at Lana and Arentorp, we found that especially the near infrared was quite much lower compared to the other drones. And also if you use some kind of other type of calibration, you would increase the near infrared here to something that is actually quite similar to the other drones. So that is something that we could see, that there was some kind of difference between this drone and the others when we used only the incoming light sensor. And I don't think that is very strange either. So but it's something to think about. However, if you calculate indices, even if you go back, no, we can't go back. I don't go back. If we calculate indices from these different calibrations with this Mavic 3M, then much of the differences are gone. So the relationship is sort of similar in a way. So even if you use the DLS and you think, okay, the reflectance was a bit lower there, if you calculate indices, it becomes sort of similar. So that's why it can be important to use indices rather than using individual bands, because indices take away some of the strange things that you can have if you look at individual bands. So to conclude this part then, good to think about that multispectral cameras are a bit different. They have different specifications. And that means that the reflectances will be different. And so it's not strange, it's just that that's how it is. It's hard to know though what is the correct, what is correct, which camera is best. We cannot answer that. It's just that you can try to have control over your procedures and the calibrations and do the same thing, so things are sort of similar and you can compare easier with other flights that you do. This Mavic 3M had, with the incoming light sensor, we saw that it was lower reflectances, but to some extent this was reduced when we used indices. So that's very important to think about. And that means also that if you make models, very complicated models, where you use individual bands, maybe some data mining methods to make sort of predictions of different things with the drone data, then it is more easy to make sort of overfitting of models when you use individual bands, and especially if you make it with complex models. So that's why it can be advantageous to go for more general, simple, maybe a bit more not so specific vegetation indices sometimes. And that's something that Kristin will talk about.
Yes. Okay, so now we will talk about the research project that is called Target N, and that is about precision agriculture, and it is about how to develop models for decision support systems for variable rate application of nitrogen, so that nitrogen rates can be adapted, spatially within a field, to the varying nitrogen status of the crop. And in Sweden, it's common to optimize nitrogen rates to each site in the field and also to each year by split application, and the latter applications during stem elongation in winter wheat, for example, you make it spatially. So then you can, for example, use a decision support system. This is a decision support system called CropSat. It's global, but this is the Swedish version in which we have implemented some models. So what the decision support system does is that it takes vegetation index maps from Sentinel-2 and translates them to supplementary N-rate maps, prescription files that can be used in the tractor to variable rate application of nitrogen. So to develop these models that translates the satellite data to the prescription files, we need to have known supplementary N rates together with known reflectance. So, and known optimal supplemental N rates, that is something that we have in field trials. This is a nitrogen fertilization trial with a plot size of about 2 × 10 meters, a very common field trial size. And the black squares here is the 20-meter resolution of the Sentinel-2 satellite images. And the image we see here is unmanned aerial vehicle orthomosaic with a few centimeters resolution. So what we see here is that we have a scale problem if we want to directly link satellite data with the ground truth data here, the known supplemental N rates. So how to do that? Well, we use drones. We use this Maya camera with 9 bands that with the same specifications as the Sentinel-2 that Mats already introduced. And we use that to collect reflectance data in the trial podlots and build the models from that, implement the models in the system, and then apply them on the satellite data to generate the prescription files. So what did we do? We went ahead and collected some data in field trials, and we did that for 3 years and in 2 crops, winter wheat and spring barley, 13 trials per crop together or over the 3 years. And these trials were nitrogen fertilization trials with 6 nitrogen rates and 10 different varieties. And the data we used and will be presented here is during stem elongation. So from the collected reflectance data, we computed a list of vegetation indices, multispectral, RGB indices, also absolute canopy properties. We used some biomass indices, some nitrogen status indices, some protein indices, and we also developed some new indices. And to do that, we plotted the optimal supplemental N rate in the different bands of the sensor, or rather, this is the R square, the squared correlation coefficient between the applied N rate or this optimal N rate and the reflectance. So you can see that here it's a strong correlation between our target variable and the reflectance in this band. A very poor correlation in this band, and again a strong correlation here. So we decided it's good to use these bands, and we decided that this band is probably good to use for standardization. So we created a number of indices based on these bands too. Okay, so then we need models. We need to models to translate the vegetation indices to supplementary N rate. And if we think about the intended application, we want to implement the models in a system that is to be used by farmers anywhere in Sweden, not just at the fields where these trials were conducted. So we need something that models that work reasonably well for very many cases, rather than something that works very well in the trials where we did measurements. So a little bit like these shirts, we are more looking for a robust model that has a decent fit in most cases, rather than something that is very tailored and complex and does maybe not work well in new cases. So we developed the models, and there are many models, and we wanted to find the one also that works well in the new cases. And to do that, one should think about how to design the evaluation of the models. And we did leave one entire trial out, cross-validation, because if you only leave a trial plot out, also you often end up with these overfitted models. But I think it's important to do a quite hard validation, leaving entire trials out if you want to find the models that work for new trials. So what do we see here? This is some evaluation statistics for winter wheat and for malting barley. We see a value called E, the Nash-Sutcliffe Valley modeling efficiency. If it's 1, you have a perfect fit when comparing with the left out trials. If it's 0, it's just as good as the mean and as the observed data. So you want a high value for this, and you should look at the blue symbols for the E value. And the mean absolute error is the error in kilos of nitrogen per hectare. So a good model has a high blue symbol and a low white symbol. Here are the different vegetation indices we saw in the previous table. The triangular symbols are RGB indices, and the circular symbols are the multispectral indices. So we can note a few things here. For example, the RGB indices performed less well than the multispectral indices. We can see that this NDVI index, that is a quite common index, it was not the best for this application. There were many other indices that outperformed it. And we can also see that there are many indices that performed about equally well, also reflecting the fact that they are often very correlated. And so many are in the top here. And then you can also make other considerations when deciding which one to use. Okay.
Okay, and one such consideration in this case is if the drone model is transferable to a satellite image, because in this case, what Kristin talked about was to develop a model that was going to be used in a satellite-based decision support system. So, and in that case, we must also know if the drone data that we collect is how it's related to the satellite data. So we did some comparisons. It's actually quite difficult to make such a comparison, we found. And we have also seen in the literature, there are some examples, and sometimes they claim it doesn't work at all, and sometimes it works. And so it's a bit challenging. I think it depends on how you do it, and if you're maybe a bit lucky also with the weather, and also maybe the quality of the satellite data. I think that's one of the crucial things here, that the satellite data, it's very hard to know exactly, especially if you're down on the pixel level. It's quite difficult to know exactly if it's, I mean, there is some uncertainty in the position. And so the content of a pixel is really influenced by the surrounding to some extent. And there is some difficulties with this. And especially you compare with drone data, they are extremely exact in position maybe. So it's a bit challenging. But in this case, with the graph you see here is the average of 32 drone flights over about 2 hectare areas. So this is the average of 2 hectare areas. So it's not, and then it's a number of Sentinel-2 pixels then are averaged in this case. We have also looked at individual pixels and everything, and it creates a lot of noise. But if you sort of start averaging, then you will, we think at least, it will give you the general correlation. So in this case, it looks really nice actually if you do this averaging. So with this index, the NDRE based on the band 7 and 5 in this case is very well correlated between the Sentinel-2 and Maya S2. So that's one of the indices that was best in Kristin's list also. So that's actually used in the system. But what if we use another sensor, for example, Mikkelsen's Red Edge, which doesn't have exactly the same bands as Sentinel-2 then, but it has a near infrared and a red edge band. And if we compare those in the same way, then you can see that it's also very well correlated, actually. But it's a bit off from the one-to-one line, which you can expect. But this means that you could also use this camera for doing such a thing as we did with the Maya camera. So as long as you have a good and stable relationship that is known, then you could try to do this if you're interested in doing it. What is important when you do this relationship between the drone and the satellite data is that you are, especially in an agriculture crop, you need to be very close in time. We see that if you have more than a few days, we have written here, maybe it depends on the crop, but then if it's more than, it starts to become extra noisy and more difficult to see the patterns. And also simple vegetation indices are easier to make it work with, I think. And also 1 or 2 flights only, and especially if you look at the individual pixel level, then it's a bit of a challenge. So I think as many flights as possible and to try to do some averaging, then you have a good chance to find a relationship if there is one.
Okay, so we have a model and it's implemented in a system. And this is just a reminder that a model doesn't know everything. The farmer knows certain things about his or her field. For example, there may be a spot here, for example, the low vegetation index may be due to something else than nitrogen deficiency, and the rate should really be 0. So it's good if you can draw on the map and set a 0 rate here. Maybe you want to, on average, increase the rate, or maybe set the maximum or minimum. So I think the general model together with the low will make the best solution, and that user interactivity should really be possible in systems where you implement models like this. So just a few summary notes here of what we learned from this project is that, well, drones, they were really useful to derive models and based on field trials when we want reflectance-based models or index-based models for systems. We could overcome the resolution issues, and systems needs robust models. So test models in independent sites and strive not for the overfitted, very complex models. We found that it was possible to develop new indices by looking at correlation spectra with a target variable. So that is one thing that you can do if you want to develop new indices. And I want to point out that user interaction is very good in decision support systems. The project is described in this publication if you want to read the details later.
All right. Thank you, Mats and Kristin. So that were our presentations, and now we'll answer the questions. So we got 25 questions in total. I just wanted to also mention that if you're just considering starting using the drone imagery in your work, in your research especially, you might find helpful the ebook that we have on our website. So you can just go over to solvi.ag and download. That will give you an overview over like what hardware you should use, how you should collect the imagery, and so on. But now let's dive into the questions. So there were a few questions along the same lines there, and it's kind of a recap that you Mats talk about. So when should you use just panels? When should you use the light sensor? When should you use both? Can you talk on that?
That's a good question. I don't know if maybe you have some comment on that. I think the most important thing is to use the same. So you don't, because you can see that there are differences. You get some differences when you use the different methods.
Right.
We always use the field panels because that's what we do. But we have seen that if you have, for example, the Mica Sense Altamore Red Edge, it doesn't really change so much. So I would say that panel works quite well also. The Maya camera doesn't have a specific panel, so we use the field panels. And it feels a bit, I think it's a bit nice to have the field panels, because then you can if you have a small area, as we often have, we like a field trial or something, then if you place a number of those panels in the trial, you can make those relationships between reflectance according to the panels and the mosaic that you create, and then it's nice to see when it sort of works very well. If it doesn't work well, then you can think that there is some issue with the mosaic, for example, or the images. So I think it's a bit depends. I think it depends on the drone that you have.
Yeah,
to do the same.
I can talk a bit from our experience, and I think that's what Micah Sans, for example, recommends. So to always use a panel, as it anchors the reflectance to the known reflectance of the panel. And then DLS is usually like supplementary data that can help correct the reflectance if the light condition change somewhat during the flight. So for example, if the sun shines through the clouds and the intensity of the light changes, that's where I think the DLS is primarily useful. It will not help if you have like rolly clouds. So if it's sunny, one part of the flight, actually a problem that we had when we collected imagery with Mats in this piece field. So the clouds were coming and going and covering the sun and introducing the shadows. So that's the worst light conditions to capture the imagery, and neither panel nor DLS will help in those situations. Now DJI doesn't provide any panel, so they say calibrate imagery with DLS, and we have seen that at least in our tests, which is quite small scale, but still from our experience, the reflectance is somewhat lower than when you calibrate with the panels. And if you are to calculate just simple vegetation indices like NDVI or NDRE, which are essentially a ratio index, it doesn't seem to make much difference, as we have seen in those charts. Because if all the reflectance values are slightly but consistently lower than when you calibrate with panel, the ratio indices will be very close. But if you use that just raw reflectance or use a bit more complicated formulas like MSAV2 that Mats showed, which make a certain assumptions and have some very specific numbers that represent the calibration, then it might make more difference. So if you have a panel, I would recommend to always using it. But then also it, of course, like depends on the specific use case. If you just want to like map a production field and spot the variations, it might be an overkill. But if you're dealing with research and comparing data over time, I would say panel is a must. And then there was also one question here about like if you change the batteries during the flight, if you should take the images of the panel between those changes. So that I would say depends on like if the flight time is spread over a longer period of time, and then if the flight conditions change somewhat, then it's recommended to take the pictures like in between the landings, so you have more reference points that you can use then for the calibration. And in Solvi, for example, this will be handled automatically, so you just upload all the images with the panel before, after the flight, in between the battery changes, and they all will be used for calibration. There was one interesting question here that I think you, Mats or Kristin, can answer. Does the leaf structure affect reflectance? For example, if it's grass leaf or broadleaf?
Yeah, I'm sure it does.
Yeah.
Yeah, I don't know how though, but I mean, it's I'm sure it affects the reflectance.
Yeah, and I think you have even in one of your slides there that leaf structure also affects the reflectance there. Okay, have you ever worked with the identification of alien vegetation? If yes, were you able to figure out which indices or which type of indices work the best for this? So I think it's more about like, can you differentiate different species, different types of vegetation using reflectance or indices?
Yeah, sure. Which what was it, a specific crop that was asked for? I didn't hear.
No, just if you can identify alien vegetation.
Yeah, alien. Okay, weed and stuff then. Yeah, that's of course possible to do. It might be difficult though. But I mean, it should be possible to do it, and some people are doing this. And yeah, which indices? I don't know. I think it can be good to try to to look at the data really to build some models. I think it can be maybe difficult with general models in principle, but to apply some index-based model, I think. But for a local field, then if you do some calibrations, then I'm sure it's possible. But can be difficult to make a model that is applicable to all fields in a large area, I guess, because it's so many things that correlates with each other.
Okay, great. Great. And I think the next question can also be relevant. So have you also carried out analysis with thermal camera, for example, to estimate crop water stress index for comparison?
We haven't done much on that, actually. So I must say that other people have done much more.
Yeah, but there is some research about that. So yes, thermal imagery can be used to analyze water stress. And there should be.
We have used only the Altum camera with the thermal sensor, and it's sometimes it seems to work very well, and sometimes it doesn't. So it's a bit, maybe it depends on, maybe you have more experience, Igor, on that, what effects. But I mean, if you have weather conditions, maybe wind and stuff, so it feels like it's a bit tricky sometimes to use the thermal camera.
Yeah. I don't have like very specific study to references, but from the imagery that I've seen, like across multiple locations and fields and geographies, you can obviously use thermal imagery. You can quite clearly see the differences if there is more moisture in the soil, for example, right after the watering of the specialty crops. There are significant differences, and cameras like MicaSense Altum, or if you use Mavic 3 Enterprise with thermal camera, they will highlight those variations, and dry soil without any moisture will typically show much higher values. So in that sense, I think thermal imagery can be useful for sure. Okay, so yeah, we have quite a lot of questions here now at 44, so I don't think we will be able to answer all of them, but we can follow up after the call. Maybe we can just take 2-3 more. So there are a few questions. So where you can buy the panels, and that's the tricky part. So usually they are supplied with the sensor. So if you buy MicaSense Altum or Red Edge, you will get one with a sensor, and then if you want to buy it standalone, I think you need to provide your camera serial number. But I think that Centera, so the company that manufactures the sensors and also has its own software to process the imagery, I think they have recently started shipping their own panel that can be bought standalone. So that could be the possibility. But otherwise, it can be a bit tricky to find one for sure. All right. Are there any other questions, Mats and Kristin, that you would like to answer there? The list is quite long.
Yes, it was a very long list. Exciting. Some questions about Solvi, and maybe something that you can.
Yeah, so there were, I think, a few questions on like how it works in Solvi, and as I showed in one of the slides, so we do support calibration with both DLS and panels. If you don't have a panel, the DLS will actually be used by default, because as Mats showed in one of the slides there, not doing any calibration at all produces very, very funny numbers. So if you don't have a panel, at least using DLS is what you should do, and Solvi does that by default. So at least, even if it doesn't show the exact same numbers as when you use panel, it kind of calibrates the numbers relative to like what they are during the date of the flight, time of the flight. But then if you have a panel, you can just upload the images with the panel, and it will be identified automatically and used during the calibration. And then if you provide the panel, then you can choose whether you want to use the DLS or not. Okay, let's see.
There was a question about what's the difference between the Altum panel and the field panels. Yeah, it's very different. Maybe did you say something about how to do the calibration there, Igor? Or?
With the Altum, or so I think the difference was more about the graph. What the Altum panel? What is field panels? So Altum panel is the one that we showed in the pictures there, the one that ships with MicaSense sensors. Field panels is panels that SLU acquired from a company from Finland, Mosaic Mill, I think their name. Those are custom-made panels that are large in size that they place in the field, and they are much better visible. So you don't actually take the pictures like you do with smaller panels with the drone before and after the flight. You just place the panels in the field, fly it, and then you can clearly see those squares. How big are the Mats, these squares?
3 by 50, I think.
Yeah, so they're well visible in the imagery, even if you fly quite high. And so Solvi doesn't support those panels, but you must have a procedure on your side on how to calibrate based on that.
We use the like empirical line method, I think it's called.
Okay.
Yeah.
There's one interesting question that I think can be relevant to your research. Can you elaborate on how you calculated the protein index and what fraction of the vegetation this includes?
Oh, there are many different vegetation indices, and if you want the equations, you can look up they are presented in the paper. So I think that's easiest. There is a link in the presentation when we share it.
Okay, great.